Hello and welcome to Woven Chemistry. I'm Jean Weaver, and in this video we're going to talk about thermochemistry, a topic I know that challenges a lot of high school and college students alike. We're going to take the general concepts and we're going to look at them from both the macroscopic and the microscopic perspectives and hopefully weave together for you a much stronger understanding of these concepts. Let's get started. Let's take a simple question for warm-up. We've got an ice cube sitting on the counter. What's the temperature of that ice cube? Can it be any range of temperatures, or is only one temperature possible? Well, it can be any temperature below and including 0 degrees Celsius. Let's assume that it's minus 20. Okay, so assuming that it's minus 20 and that it warms to 0 degrees Celsius, and let's assume it doesn't get any warmer yet. I've got 4 questions here about the particles. What happens to the particles as the ice warms but before it starts to melt? So pause the video and jot down your answers to these questions. So in the lower left here, I've got a diagram of water at the microscopic level. You can see that the particles are all pretty organized. That's typical of solid water. First question, does their movement change? And the answer is yes. Okay, they're not really moving from side to side, but they vibrate. Okay, and what I mean by vibrate is they're going to move kind of like this. When the sample gets warmer, they can vibrate faster. Does the arrangement of the particles change? Well, you just saw in that animation, they stay arranged pretty much the same, so that's a no. Does the structure of the particles change, or are bonds broken or formed? No. If that were the case, then we would see that the O wouldn't be connected to the H anymore. It wouldn't be H2O anymore. Or perhaps 2 molecules would join together like this, and then in that case it would be H4O2. But we know that it's still water, it's still H2O as it's warming, so the answer to the last 2 questions is no. Okay, another question. What happens to the heat that the particles absorb? Okay, this tends to be pretty tricky, so think this one through and join me when you're done. Okay, when particles absorb heat, or when a substance absorbs heat, does it continue to be heat? I know this sounds weird, but it does not. Substances can absorb or release heat, but they don't have heat. It turns into another kind of energy. Does it turn into kinetic energy? Well, the answer is yes. Kinetic energy is energy of motion, and we just saw that those particles will vibrate faster as the sample warms at the macroscopic level, so the kinetic energy goes up. Now, does it also turn into potential energy? In this case, no. Potential energy is stored energy in bonds and IMFs, and since those don't change, there's no change in potential energy. Okay, a few more questions, okay, pertaining to where this heat comes from. So the heat comes from the air, and I've drawn in air particles here to kind of help you visualize what's going on here. What happens to the air when it loses heat to the ice cube? Well, that heat is going to come from the kinetic energy of those air particles, and as they hit the ice cube, they're going to transfer some of their kinetic energy to the ice. They're going to lose kinetic energy at the microscopic level, and at the macroscopic level, the temperature of that air will drop. Now, how could we make that ice cube melt faster? That probably didn't require a whole lot of thinking. You could put it in the sun, put it in an oven, but why does that work? Well, heat flows from high temperature to low temperature. What we say is down a temperature gradient. The larger that gradient, the faster the heat is going to flow. So to kind of help you visualize that, let's imagine this is just kind of a normal warm sample of air, and focus on this little molecule right here. Remember, they're moving around. I'm going to animate that one. And so it's moving, and it will collide with the ice the ice block. Okay. Oops. And let's see that again. Okay. So it glides, and it just kind of bumps gently, and it might nudge those particles to move a little faster. Now let's say that this sample of air is much warmer, and let's focus on this molecule right here. If it's warmer, those particles move a lot faster, and so it will hit that ice particle, the ice block, very hard, and transfer. Let me get that again. And transfer more of its energy because it's moving so much faster. Okay, now let's move on. Let's assume that it's now at 0 degrees and that ice cube is melting. Okay, first question, write a chemical equation to show what happens to the ice when it melts. Okay, actually write this down, try to get as many details as you can spot on. Okay, it's a very simple equation. We're taking solid water and turning it into liquid water, and I ask you to include the enthalpy of fusion, so you should have on the reactant side added 6.01 kilojoules. Why didn't I write kilojoules per mole? Because the equation as written with this invisible 1 here implies that 1 mole of water needs 6.01 kilojoules of energy. Okay, now let's focus in on what happens to the ice particles as the cube melts. Okay, pause the video and think through these answers before you listen to mine. Okay, to help us out, let's visualize solid ice and liquid water at the microscopic level. Do the bonds break? Well, we can see that they don't. It's H2O in both drawings. Do the IMFs change? Well, the answer is yes, but let me show you why. The dotted lines here represent the IMFs, okay, and we can see that those are holding these particles rigidly in their spots. In the liquid, the IMFs are kind of here, there, and everywhere. So what happens as the sample as the sample melts, is those particles are gaining energy, and it's allowing those particles to overcome the IMFs that are holding them in place. Now we can see that the arrangement of the particles changes, but since the energy is going to overcome IMFs, not to increase the kinetic energy, it's one or the other, it's never both, those particles do not vibrate faster. Okay, so microscopically that heat is being used to overcome IMFs. Macroscopically, it's being used to cause a phase change. Okay, macroscopically and microscopically there's one kind of change, not both. Okay, a few more questions for this melting process. Pause the video, think about your answers before you listen to mine. So what happens to the temperature? Well, we said that there's a phase change now, and that energy is going for a phase change, not a kinetic energy or a temperature change. So as it's melting, since the temperature is the same, that means that there's no change in kinetic energy at the microscopic level. Now, what happens to the potential energy of the ice as it melts? Well, that's going to increase, okay, because the particles are overcoming those IMFs that hold them in place. So I've got some water molecules here that are held together by like a magnetic force, and it takes energy for me to pull them apart. Okay, that's not a lot different than if I have a rubber band. Okay, I have a rubber band and it takes energy for me to pull it apart. This is the high energy state. Just like with the water molecules, this is low energy. If I pull them apart, this is high energy. Going back to my rubber band, when it's pulled apart, we know that this is a high energy state because if I let go and let go properly, it's going to fling across the room. Okay? Okay, so now let's assume that it's completely melted. Our house is 20 degrees, and we've got about 5 or 6 more questions. Okay, jot down your answers to these and then come back and listen to mine. So when the ice has completely melted, okay, it's going to warm. And here's what's going on. We've got 0-degree water and the room is 20 degrees. Well, we've got a temperature gradient. So heat will flow into that water, and that heat will get converted into kinetic energy, and it will warm the water. So 13, the kinetic energy is going to increase. Do the particles move faster? Well, yeah, that's what kinetic energy is all about. Do the bonds break? Well, when water warms, it's still water, so the bonds do not break. Do the IMFs change? Nope, it is still liquid water, so no change in IMFs. So if the IMFs and the bonds don't change, then that means the potential energy does not change. So maybe you're feeling a little bit confused about, what goes up and potential energy, kinetic energy. So I've made a summary diagram here. Let's assume this gray box is our object, and heat is going to flow into our object. Let's think about this from the microscopic and macroscopic perspective. That heat can get converted into one of two things, not both at the same time. kinetic or potential energy. If it goes to kinetic energy, that will make the particles move faster, right? Kinetic energy is 1/2 mv, v for velocity, squared. At the macroscopic level, when the particles move faster, the temperature goes up macroscopically. Okay, another option is for the potential energy to go up, and if that happens, the particles will end up with more freedom of movement, which means they're overcoming their IMFs, and macroscopically that means a phase change, boiling or melting. Now, potential energy can also take the form of bonds changing, breaking or forming, and when that happens, we have a chemical reaction. Now, in this video, we've only talked about the phase change. Okay, if you want to see what this diagram looks like for when something is cooling, I've got this diagram. Everything is opposite. And with that, that concludes this video. I really recommend that you come back and watch part 2 because we're going to take all of these same concepts and now apply them to heating and cooling graphs. Okay, so again, thanks a lot for joining me, and I hope to see you again.